Dear friends, before going into the subject heat and mass transfer, let us see how it is different from thermodynamics. So, in thermodynamics, we learned about processes, okay, different types of processes or energy interactions. And processes means it is basically equilibrium process. Energy interactions, amount of energy needed. Is it amount of energy needed to keep the system at a specified conditions. Actually, the thermodynamics has laid a framework to study the subject heat and mass transfer. In heat and mass transfer, we deal with non-equilibrium process, non-equilibrium processes, or non-equilibrium phenomenons. Huh? Now here we learn about only one energy, that is one of the internal energy, that is heat energy. We learned about the amount of energy needed. Here one more thing that we add, that is time. We relate the energy with time. So we don't know, we did not discuss about if some amount of energy is needed, how much time I need to add this energy. We did not talk about all those things. Now here comes the time, the relation of energy with time, that is not something called as we in engineering, that is rate. Okay, so this is how transfer is different from thermodynamics. Now let us discuss the first law of thermodynamics. We always use this law even in our life. We all know that the conservation of energy principle, that energy can neither be destroyed nor be created. It can change from one form to another. And when this first law is applied on a system, simple compressible system. What is a simple compressible system? That is when we neglect the effects of magnetism, motion, gravity, surface tension. When we neglect all these things, the system will become simple compressible system. And when we apply that, the first law written, the total energy entering into the system minus total energy leaving the system is equal to the change in total energy of the system. With simple example, I will make you understand that. Suppose there is a box, and suppose I put 10 pieces of of chalks. This is equivalent to something that is coming into the system, and this is something that is going out of the system. Suppose there are two chalk pieces that is going out of the box. Okay. Now what is the change inside this chalk box? That is 10 minus 2, that is equal to 8. So that is the change happened that inside the box. The same way some energy will be coming in. Suppose it is 100 joule. 100 joule is coming in. Okay, that is coming into the system. This is my system. And suppose 30 joule is going out of the system. What is the change inside the system? It is 100 minus 30. 100 minus 30, 70. So 70 is the change inside the system. That is simply the first law when applied to the simple compressible system. Now in the rate form also we can write that. We just have to add the rate here, that is rate of total energy coming into the system minus rate of total energy leaving into the system is equal to rate of change of total energy of the system. Mathematically, how can we write it? If there is no rate, I will not put E dot. Instead, E in minus E out is equal to dE system. Now, if it is the rate form E dot minus E dot in minus E dot out is equal to dE system by dt. So this becomes the rate. Now suppose that if the system is steady, if there is no change with respect to time, then it is called steady process. Then E dot in will be equal to E dot out, since dE system by dt is equal to 0. So that is in the right form for a steady process. Now let us see how we are going to use this equation in heat transfer. Some heat will be coming in minus this Q out heat that is going out plus E generated. This is my net heat transfer. Heat transfer. This is heat generated. We will study this thing in detail. Heat generation means heat generation because of some chemical reactions or some nuclear reactions. Some heat will be generated inside the system also, so that will be equal to delta E system. So that is the change in thermal energy of the system or heat energy of the system. Next we will see what if it is applied on closed system. It will be nothing but E in minus E out is equal to delta U. There is no work, delta U, and this is equal to mCV. Now if it is a open system, that is energy balance for a steady flow systems. In practice, basically we are dealing with heat transfer system, that is radiators are there, then heat exchangers are there. So how to apply that? I will show you an example. So if this is a pipe and I select this as a control volume, this is my control volume, and some fluid is coming in, suppose, and this is the fluid that is going out. This is coming with some heat energy and this is going out with some heat energy. Then minus E out is equal to m delta H. We know that H is equal to nothing but U plus PV, where U is the internal energy of the fluid and PV is the flow energy of the fluid, that is the energy needed to maintain a flow through this pipe. And we know that enthalpy is nothing but H is equal to m dot Cp dt. So this will be equal to nothing but m dot Cp dt.